Hello viewers, there are many objects which are inaccessible to us height wise. For example, the top of a tree, pole, mountain peaks, an aeroplane flying at some height, and distance wise, for example, width of a river, a ship, the distance of a ship from the shore, as the case may be. A right angled triangle provides us an easy way of solution for finding these unknown heights and distances given any two other sides using Pythagoras theorem. But finding out distance is more inconvenient than finding out an angle. So, how does an angle help us in finding out unknown heights or distances using a triangle? The branch of mathematics which deals with the measurement of the sides of a triangle is called trigonometry. It has formed from the words trigonon meaning triangle plus metron meaning measurement. Trigonometry is generally used in solving problems related to astronomy, engineering surveys, navigations, etc. To understand this, let us perform this experiment. These are two right angled triangles with the same base angle. That means the angle, the acute angle in both these triangles are equal and one angle is 90 degree in both these triangles. The two triangles are similar by a similarity. That implies that two triangles are similar, then their corresponding sides will be proportional. That means in this case the ratio of the perpendicular upon the base of this triangle will be equal to the ratio of the perpendicular upon the base of this triangle. So, if the perpendicular in the first triangle is 10 units and the base is 8 units, then this ratio will be equal to the perpendicular which we have to find out, and we have for this moment taken it as x upon the base, that is 16 units. That gives us the perpendicular of this triangle, that is x, is equal to 160 upon 8, which is equal to 20 units. Similarly, if there is another right angle triangle having the same base angle, that is theta, then in that triangle also the ratio of the perpendicular to that of the base will be equal to the ratio of the perpendicular to the base of these triangles. That implies that in similar triangles, using ratio we can find out unknown sides of a triangle for a particular angle. These ratios have been in use since early times. They have been termed as sin theta, cos theta, tan theta, where theta is an acute angle in a given right angle triangle. This is a right angle triangle, right angled at B. This is the angle of reference, we call it as theta. Then the side AB is called the perpendicular, the side BC is called the base, and the side AC is called the hypotenuse. But in case we take angle A as the angle of reference or theta, then in that case side BC becomes the perpendicular, side AB becomes the base, and side AC becomes the hypotenuse. So, in order to avoid this confusion, we say that if this is the angle of reference, then AB is, instead of calling it as perpendicular, we call it as the side opposite to the angle theta, and BC we call it as the adjacent side instead of saying that this is the base, and AC remains as the hypotenuse. In this case, sin theta spelled as SINE, in brief we call it as SIN, but read it as sin theta. This is the ratio of the side opposite to the angle theta to that of the hypotenuse. In this particular triangle, sin theta is AB upon AC. Cosine theta spelled as COSINE, in brief, which is written as cos theta and also read as cos theta, is the ratio of the adjacent side to that of the hypotenuse. In this particular case, cosine theta or cos theta is BC upon AC. Tangent of angle theta, which is in brief called as tan theta, is nothing but the ratio of this side opposite to the angle theta to that of the adjacent side. In this particular triangle, tan theta is equal to AB upon BC. Besides sine, cosine and tangent of an angle theta, there are three other trigonometric ratios named as cosecant, secant and cotangent of an angle theta, where cosecant of angle theta, which is written in brief as cosec theta, is equal to the ratio of the hypotenuse to that of the side opposite to the angle theta. In this particular case, it is AC upon AB, but we know that the ratio of AB upon AC is sin theta. So, this ratio, that is AC upon AB or hypotenuse upon the side opposite to the angle theta, is reciprocal of sin theta, or we write cosec theta as 1 upon sin theta. Then secant theta, which is in brief called as sec theta, is the ratio of the hypotenuse to that of the adjacent side. In this particular case, it is AC upon BC, but it is again the reciprocal of the ratio of the adjacent side upon hypotenuse, which was cos theta. So, we write sec theta as 1 upon cos theta, and cotangent of theta, which is in brief called as cot theta, is the ratio of the adjacent side to that of the side opposite to the angle theta. In this particular triangle, it is BC upon AB. Again we find that this ratio is the reciprocal of the ratio of tan theta, which was the ratio of the side opposite to the angle theta to that of the adjacent side, and therefore, cot theta is written as 1 upon tan theta. Out of these 6 ratios, if any one of the ratios are given, we can find out the other 5 ratios. Let us see how. Suppose we are given that sec theta is equal to 5 upon 4, and we have to find out rest of the 5 ratios. For that, let us draw this right angled triangle. This is right angled at B, and we have taken this angle C as the angle of reference, that is theta. Now, since we are given that sec theta is equal to 5 upon 4, then sec theta we already know, that is the ratio of the hypotenuse. So, hypotenuse will be 5 units to that of the adjacent side. So, that means BC will be 4 units. We have to find out the side AB. If we can find this side AB, then we will be able to get all the 5 ratios. Now, since this is a right angle triangle, therefore, we can use Pythagoras theorem, which says that AB square, that is the side opposite to the angle theta, plus BC square, that is the square of the adjacent side, is equal to the hypotenuse square. AB square we have to find out. So, we have AB square is equal to AC square minus BC square. We have taken BC square to the right hand side. This implies AB square is equal to AC square, we are given, AC is given as 5. So, AC square will be 5 square minus BC is given as 4. So, BC square will be 4 square, which is equal to 25 minus 16, which is equal to 9. This implies that AB is equal to under root of 9, which is equal to 3. So, by Pythagoras theorem, we have found the side AB, which is equal to 3. So, if this side AB is equal to 3, then we can find out the other 5 ratios. In this case, first of all, we will have sin theta. Sin theta is nothing but the ratio of the side opposite to the angle theta to that of the hypotenuse. Now, here the side opposite to the angle theta is 3 and hypotenuse is 5. So, sin theta will be equal to 3 upon 5. Cos theta is equal to, it is the ratio of the adjacent side to that of the hypotenuse. So, it is equal to 4 upon 5. Tan theta is equal to the ratio of the side opposite to the angle theta to that of the adjacent side. So, this is equal to 3 upon 4. Cosec theta, it is the ratio of the hypotenuse to that of the side opposite to the angle theta, that is 5 upon 3. From here also we can find out cosec theta, because we know that cosec theta is reciprocal of sin theta. So, if sin theta is 3 upon 5, then cosec theta becomes 5 upon 3. Sec theta we are already given, and cot theta, it is the ratio of the adjacent side, that is BC, upon the side opposite to the angle theta. So, this is 4 upon 3. You can again verify that since cot theta is reciprocal of tan theta. So, if tan theta was 3 upon 4, then cot theta becomes 4 upon 3. Thus, we found that given any one ratio, we can find out the values of other 5 ratios. As we have already said earlier, that finding out a distance is more inconvenient than finding out an angle. Here is a model of an instrument called clinometer for measuring an angle or an inclination. Suppose this is the baseline. If you want to measure the angle, first of all we have to read the angle made here 70 degree here, then we will measure this or incline it towards the top of this object, and again see the readings here, it is 120 here. So, the difference between 70 and 120, that is the angle of inclination, in this case is 50 degree. A clinometer usually do not give us the accurate value. A more sophisticated instrument which gives us accurate value is called sextant. It is usually used by navigators and in engineering survey purposes. let us prove some more important results called trigonometric identity. Do you know what is an identity? An equation in one or more variable is said to be an identity if left hand side of the equation is equal to the right hand side of the equation for all values of the variables for which both sides are defined. For example, consider the equation sin square theta plus cos square theta is equal to 1. Here, if theta is equal to 0 degree, then we know that sine of 0 degree is equal to 0 and cos of 0 degree is equal to 1. So, for theta is equal to 0 degree, we find that left hand side of the equation, in short I am writing EQ, is equal to right hand side of the equation. Again, for theta is equal to 90 degree, we know that sine of 90 degree is equal to 1 and cos of 90 degree is equal to 0. So, again we find that for theta is equal to 90 degree, left hand side of the equation is equal to right hand side of the equation. That means the equation is defined between 0 and 90 degree, including the values 0 degree and 90 degree. So, we say that theta is defined in the interval 0 to 90 degree. Now, for any other acute angle, let us take the angle, acute angle ABC. We have taken this angle theta here. Let us take any point x on this side AB other than A, and from x let us drop a perpendicular to the side BC. This perpendicular is xy. Then this triangle XBY is right angled triangle, right angled at y. Now, in this case also sin theta will be equal to the side opposite to the angle theta, that is xy. Sin theta is equal to xy upon hypotenuse, that is bx, and cos theta is equal to the adjacent side upon the hypotenuse, that is by upon bx. This implies that sin square theta plus cos square theta is equal to xy upon bx whole square plus by upon bx whole square. This is equal to, I can take LCM bx square. So, here we have xy square plus by square, but this triangle XBY is right angle triangle, and therefore, we can apply Pythagoras theorem, which says that xy square plus by square is equal to bx square. So, from this triangle XBY, triangle XBY, because it is a right angle triangle, we have xy square, if this is the figure, xy square plus by square. So, plus by square is equal to bx square. So, now this expression xy square plus by square can be replaced by bx square as we have just now proved. So, this is equal to bx square upon denominator was already bx square. So, this is equal to 1. So, thus we proved that sin square theta plus cos square theta is equal to 1. This equation holds for every value of theta, or it is satisfied for all values of theta, and therefore, by a condition this equation, that is sin square theta plus cos square theta is equal to 1, is an identity. Consider another equation. 1 plus tan square theta is equal to sec square theta. We would like to check whether this is an identity or not. Again here, for theta is equal to 0 degree, we have tan of 0 degree is equal to 0, because tan is nothing but sin upon cos, and sec of 0 degree is equal to 1. Therefore, putting these values here, we find that for theta is equal to 0 degree, left hand side of the equation is equal to right hand side of the equation. Next, let us consider for theta is equal to 90 degree. When theta is equal to 90 degree, we find that for 90 degree tan 90 is not defined, and sec 90 is also not defined, because sec 90 becomes 1 upon cos 90. Let us write it. Sec 90 is 1 upon cos 90, and we know that cos 90 is 0 and 1 upon 0 is not defined. Similarly, tan 90 is not defined, that means for theta is equal to 90 degree, this equation is not defined. So, the equation is defined for theta greater than equal to 0, but less than 90 degree. For any other angle theta, we know that tan theta is equal to sin theta upon cos theta, and sec theta is equal to 1 upon cos theta. So, left hand side of the equation, which was 1 plus tan square theta, becomes 1 plus sin square theta upon cos square theta. This is equal to, I can take cos square theta as the LCM, cos square theta here, and this becomes cos square theta plus sin square theta. But just now we have proved that sin square theta plus cos square theta is equal to 1. So, we can use that identity here and replace this cos square theta plus sin square theta by 1. So, this expression becomes 1 upon cos square theta, and we know that 1 upon cos square theta is nothing but sec square theta. So, thus we proved that 1 plus tan square theta is equal to sec square theta. This equation is satisfied for all values of theta, and therefore, it is an identity. Look at another equation. 1 plus cot square theta is equal to cosec square theta. Again, we would like to see whether it is an identity or not. So, first of all, see, for theta is equal to 0. When we put theta is equal to 0, we find that cot theta is not defined. Can you tell why? Because cot theta is cos theta upon sin theta, and sin 0 is 0, cos 0 is 1. So, 1 upon 0 cannot be defined. Similarly, cosec theta is again not defined because cosec theta is 1 upon sin theta. For theta is equal to 0, it becomes 1 upon sin 0 and sin 0 is equal to 0. Therefore, 1 upon 0 is not defined. So, for theta is equal to 0, the left hand side as well as the right hand side of this equation is not defined. Let us see for theta is equal to 90 degree. When theta becomes equal to 90 degree, then we have cot of 90 degree is equal to 0 and cosec 90 degree is equal to 1. Therefore, again we in theta is equal to 90 degree, we find that left hand side of the equation is equal to right hand side of the equation. That means this equation 1 plus cot square theta is equal to cosec square theta is defined for theta greater than 0 degree, but less than or equal to 90 degree. It is defined in this interval. For any other angle theta, we know that cot theta is equal to cos theta upon sin theta and cosec theta is equal to 1 upon sin theta. Now, the left hand side of the equation is 1 plus cot square theta, which can be written as 1 plus cos square theta upon sin square theta. Again from here we can take sin square theta as the LCM. So, writing sin square theta here, we get sin square theta plus cos square theta, and we have already proved that sin square theta plus cos square theta is equal to 1 is an identity. So, replacing this sin square theta plus cos square theta by 1, we get the expression 1 upon sin square theta. We know that 1 upon sin theta is cosec theta. Therefore, 1 upon sin square theta is equal to cosec square theta, which is the right hand side of the equation. Thus, we find that 1 plus cot square theta is equal to cosec square theta. These are three basic identities which are further used in proving other identities. Before we finish today's lesson, let us have a quick recapitulation of what all we learned today. We learned that the ratio of the side opposite to the angle theta upon hypotenuse is equal to sin theta. The ratio of the adjacent side to that of the hypotenuse is called cos theta. The ratio of the side opposite to the angle theta to the adjacent side is called tan theta, and cosec theta is reciprocal of sin theta, sec theta is reciprocal of cos theta, and cot theta is reciprocal of tan theta. We learnt about trigonometric ratios and identities connecting them today. They will be useful in finding out unknown heights and distances which are inaccessible to us in our daily life. Thank you.